Hello, everyone. Be welcome to our webinars, Mastering PID Control, the top 5 factors for optimal loop tuning. I'm Vera from Control Station, responsible for marketing. I'm based in Ireland. And before we start, I just want to let you know that here in the control panel you can input your questions and comment during the session. So in the end of the webinar, we will answer these questions. Our presenters today is Bob Rice and Damien Moreau. Bob Rice has nearly 3 decades of engineering and product management experience in the process industries. As a recognized thought leader, Bob oversees development of Control Station's award-winning suite of process diagnostic and optimizations technology. And Damien has over 20 years of industrial experience, specializing in process control diagnostics and optimizations with many manufacturers, and leveraging technical and engineering positions across key industries. For those who are new to control stations, we've been an active innovator since the 80s. Today, we are proud to support an increasingly global clientele, and our customers include leading manufacturers from across the process industries. Our agenda for today is why PID controller tuning is important, top 5 factors that influence tuning results, and your next steps. So we are going to start with a question that's going to show in your screen.
Thanks, Vera. We'll just get in on this now, and I'd ask you to consider those questions there and give an answer to one of them. How are PID control loops modeled and tuned at your facility? Just pick one of those answers. There's 4 of them there, quite obviously. Pick one that's most appropriate to your experience with tuning. It'll give us an opportunity to get a sense of the group that's here and their needs and the way they've done stuff.
Yeah, and to kind of add to Damien's, you kind of see the different type of tuning practices, which is, you trial and error, you guess. Some people have built maybe spreadsheets and look at trends and kind of have a more methodical approach. Some use software, and some push it all to outside consultants, depending on what their internal expertise is, right? And so it's always useful for us to kind of understand what the crowd has, and we can kind of tailor some of the conversation points during the presentation to those.
Yeah, indeed, it is something that's in the modern world of manufacturing, and that last one is to push it out to the consultants, the contractors. I suppose it's something that you're seeing more and more of.
Yeah.
But we'll wait for the results, I suppose, to see what feeds back onto that.
Yeah.
Okay, so excellent.
All right. So that tends to jive with kind of what our experience has been, right, Damien?
Absolutely. Yeah.
Internal use, you kind of you guess and test, trial and error tuning, keep trying until it works, right? Some people look like they use trends, probably have processes in there, and people are starting to look at software and stuff, but it's always been kind of on the back of their mind, right?
Yeah, absolutely. The changing parameters until it's good is that's an age-old, tried and tested method. It can tend to leave processes in perfect for where you are, but if the process moves at all, you'll go unstable very quickly. So it's fine if your system is very stable. The 10% down the bottom are interesting. That's growing, I think, over time. That's starting to get more and more prevalence to it, and that I think it's the realization that there's a better way. There's a more organized way, whether that's to give it to your system integrators or to start to develop a process internally. But Interesting answers.
Yeah.
We
Okay.
keep going there, Vera. Lovely. So just to kick off here, we're just looking at some statistics here to see, we've done some studies and there's some documents in the past, you can look down at the end there where the dates of these are. And you say, oh, yeah, what's that? That's nearly 30 years ago now, so that can't be the state. Well, if you think about those in your processes as to go, 20% of systems are not properly configured. That's going to happen. There was something missed in design, it got into construction and it was built and there's a miss on it. 30% of loops operating manual mode, that's across the board. We're still seeing those kind of numbers, poorly tuned, and then 85%, being, is going to feed into that. Bob, do you want to take those higher numbers? And
I'll kind of add into it. The idea that like controllers are not designed appropriately for their objectives is it drives into that top metric there, which is they're performing ineffectively in automatic mode, which means they don't have the right kind of design. You've got interacting controllers, temperature zones in your ovens, and they're all tuned fast, and they're sitting there fighting each other, and so operators drop them into manual, which contributes to that 30%. And in fact, we've done audits of and kind of analysis of some of our clients, and we're still seeing somewhere between the 20 to 30% range of control loops in manual at most facilities, right? And I would say the average today is maybe around still that 20 to 30%, and the target you should be hitting towards is 95%. Like we've got clients who have done a lot of continuous improvement and driven their process and hold loops 95% of the time in automatic. Some hit 99%. That is world class, right? But most sites are going to be in that 70 to maybe 80%.
It is hard, but it is achievable. You just have to start getting consistent with the effort. It's not just a once in a while when there's a problem loop. It does need to be a mindset change within your group.
Mm-hmm. And so next slide, Vera. I mean, what's kind of interesting is why do we even care about PID tuning in the first place, right? Yeah, we'd like the control loops to be running in automatic. That's good, but just running in automatic isn't good enough, right? The idea is that PID tuning is what kind of holds your plant steady. And if you take that kind of status quo, that poor control on the left, and you apply some tuning or some improved process analysis, you're looking at valves, you're improving the process, you tighten control, that's awesome. What that allows you to do, though, is do that optimization. You can push your process operating closer to constraints. And we've done, projects where, taking and moving degrees on like your steam loops, your glycol utility loops, 1 or 2 degrees kind of closer to those constraints, you can start to save energy. And it's that optimization that drives the value, allows you to minimize energy use, minimize waste production, maximize overall production rate, to be able to stabilize the loop and push your process to its limits. And tuning is all about that. And the way that I like to think about tuning in all of your loops is it's an orchestra, right? You got to get all the loops to kind of work together to be able to try to get your process to operate as smoothly as possible, operating close to those constraints to be able to drive additional value out of your loops, right?
Yes, absolutely. I suppose the 3 phases of that trend, you can quite clearly see the loop was not in control and it was away from set point. But that middle section there, regularly I ask customers, so why are you controlling at that set point? Because we always have been. Or why is it in manual? Because it always has been. It's habituated into it. Is somewhat. There does have to be that. How can we make it better? How can we improve it? How can we run more effectively towards that constraint? You're potentially going to make a better product there. You're potentially going to have a less energy consumption, but all of those things are going to feed into that improvement. Very good. Next slide. With those improvements, these are the kind of changes you can make. Throughput, yield, consumption, and defects. You get your throughput you know, to improve by those kind of numbers, that's a significant portion over your annualized production. You know, your yields or your quality, the energy one there is there. Like if you think of your energy consumption on a site, PIDs are the users of that energy. You know, they're the ones that are making the decisions as to how that energy is going to be used. Hot and cold water, steam, electrical power on motors. You know, if you can take 1 to 5% of those numbers, and you know, 1 to 5% is 5 to 15. They are easy achievable numbers. Ask your utilities people, what is your energy bill from your utilities building or your utilities? You know, what is 2% of that? These are really, they become really big numbers. You know, the sustainability, the quality, the improvement. Everybody accepts that we have to use energy to make product. You know, it's just being as efficient as you can with that. Bob, you want to take anything out
Yeah,
of that?
and you know, I can kind of bring it back to that last slide, right? Where we're talking about moving closer to those constraints. If you can stabilize control, and all of that variability could be considered wasted energy, and you can move those set points a degree or 2 degrees lower, kind of based off that variability improvement, and you can improve your energy consumption by 1, 2%, 3% pretty easily. I've done projects where we just looked at all the steam users and all the chilled water users, looked at all of their variability, tuned them, and then moved the set point, you know, up or down depending on if it's steam or glycol, to be able to, recover some of that energy a little bit better. And the numbers were pretty staggering, right? And just from a practical standpoint, think about how you drive your car. If you're driving nice and smooth and you're accelerating smooth and slow, you're going to get better fuel economy. I mean, yeah, it's more fun to drive when you're pushing everything kind of crazy, but you're going to drop the fuel economy on your vehicle. It's the same thing for your plant. You're going to drop the economy of the energy consumption. The more you start moving things around and going crazy with it, it can actually cause a lot of issues that can be improved with tuning and optimization, and you can start to save money, right? And that's really where we need to get to. And so then it comes down to trying to understand what the purposes of the controllers, right? What the objectives are. And so if we kind of go to the next slide, when you're talking about a control loop, it's not just, you know, hey, I got to track set point at all possible costs, right? You got to understand the objective. You got to strike a balance. You got to understand, am I tracking set points? Am I rejecting disturbances? Are you doing set point changes, load changes? You got to have to strike a balance between those, right? Tight control is nice in some cases, but it causes a lot of wear and tear, right? You got to look at settling time. You got to look at oscillations. You got to understand the behavior. You got to define the purpose of that controller. What is its goal? What is its reason? Right? And that is really a part of the controller tuning process that is typically overlooked, right? We're just going to go tune the loop, right? I can guarantee you, and you know, a lot of times commissioning, you go in, just get the darn thing running, right? But just running isn't good enough. You need to go and figure out, why is that control loop there? What is the goal? You got to have an end game in mind. What does good control for this loop look like when you think about the bigger picture, right? Defining that objective gives you the ability to go and tune the loop appropriately. And me and Damien both teach controls classes, and one of my favorite exercises, I set up a mystery process. Nobody knows what it is. And I say, tune it, make it good, right? Good is different to everybody. And if I have a class of 15 people, I can tell you that there's probably going to be about 13 to 15 completely different responses, because everybody's idea of what good control is personal, right? And it needs to be specific to the process, right? You need to define what the control objective is, which requires you to go talk to operators, talk to engineering, talk to management, kind of define what the goal, the purpose of that controller, what was its original intent, right? And it's a process, right? Trying to understand the process is important, right, Damien?
I call that my why am I here? You know, it sounds deep and meaningful, but it's the reality is, when you're standing in front of a PID, why am I here? What has brought me to this point? And you know, whether it's a new loop that you're commissioning, or it's a loop that operations have brought you over to say that PID is not working anymore. Well, you know, and you have to answer all of those questions as to what is it not doing, what is it not achieving. It's something actually that's drifted in again from our survey at the start, that 50% run tuning in manual. The likelihood is that's one of the fundamental reasons why it was working and now is not working, because the process has moved in one direction or another, or equipment has started to age, it's getting sticky, this heat exchangers are scaling, or something has changed to cause the process to move. And the manual tuning efforts tend to leave the process right at its edge, similar to the Ziegler-Nichols. You leave it at a point where it's reactive, responsive, but it's not stable. If the process moves at all, it'll drift out of it. It's something actually that I've noticed has drifted in over as our PLC processors have started to get faster and faster and more capable. Everything has sped up, and the expectation that the PID should speed up as well, in its response, has drifted in a little bit into those tunings to give these actions. Faster is not always better. You need the response I set to is respectful of the processes around it. Is it adapting to, and there's no point in having a flow controller that can respond in 3 seconds if it's feeding a heat exchanger that takes 15 minutes to react to change. There's no requirement for that flow controller to be that fast. If it's more progressive, it will allow the heat exchanger to adapt to that change, and that's what can start to cause that hunting. Next slide, please. So, good control is simple, and this is taken from Bob's comments in the previous one. Safety, impact, management, profit, longevity, and equipment. In my why am I here, I always think, okay, safety, what am I going to do here that's going to negatively affect the safety of this plant? Increase your proportional effort, double it, speed it up. It's going to potentially, it may not happen on the first time, but again, if you're going to start working the system faster, what impact has that on safety? The impact that this change has, where does it sit in your process? Where is it going to, what impact does it have if I slow this system down or speed it up? Is it where does it fit in my process? Is it a critical loop? Management is, management of your process, management from the operations, management from your manager. There's a lot of managements there, I suppose, but all have to be fed into that to go, what type of performance do we want here? We need the system to react to that temperature so that the chocolate is tempered correctly, and because that's key. The key parameter on a chocolate producing system is tempering, to get that good quality snap. Profit, we've talked about that already. Is there an energy saving function here? It's going to come from lots of places, whether it's reducing the energy push into it, reducing the oscillation. All of those are going to feed into that, making better quality product, making it slower and more stable, making a more consistent product. Bob, I leave the two last to you from
And looking at things like longevity and equipment, you want to make sure that the strategy endures, right? That it is tuned appropriately, so you're not having to deal with it every week. Kind of think about the long-term side, and don't make control strategies overly complicated when they don't need to be, right? And understand that your equipment is expensive, right? Valves and so forth, you got to balance all of that. You got to think through all of it. Now, the question that I always like to pose is, where does this information live? Where do the answers to these questions live? And the answer is probably in the minds of 20 different people at your site, right? And that's not a good answer, right? Having to go and talk to a whole bunch of people to try to, cull all this information together into what the control objective is a time-consuming process. What I would like to propose, and and those who have heard me talk before have heard me say it a million times, documentation is where this should live, right? You should build control narratives for every single control loop you have at your facility, no matter how minor it is. If it's still a control loop, there was still investment in that loop. The least you can do is at least write a document to, this is the purpose of the controller. This is what it's supposed to do. This is where it fits into the process. Here's how you should tune it. Because ultimately, the control objective is the end game. And if you're trial and error tuning, how do you know when to stop making changes to the tunings until you've defined what that end game is? So the control objective is the end game. This is what the controller should do under the most ideal circumstances. And so that's what's going to drive your tuning, is a control objective. Have we beaten this into the ground enough? right? I mean, this is the most important thing, right? It sets the basis, right? But once you've got the objective, now we can start to talk about things that allow us to generate tunings, right? So we
Just
can
to jump
talk
back
about
in
the
there, Bob,
bumping.
I suppose, sorry to jump back in, but that control objective, it's hard work initially, but it starts to pay off in that you can set your control objective for flow controllers, for temperature controllers, so that you can approach it with this standardized methodology, so every flow controller can be set like this, every temperature, so you can start to build this template almost for how
Yeah.
you approach them, but it's the documentation that does it, absolutely.
Documentation allows repeatability, right? And that's what we're after, because repeatability allows efficiency gains in the processes that we're doing, right? And so if now that you've got the control objective, let's talk about getting data and analyzing that data to generate tunings, right? And the very first thing you have to do to be able to generate tunings is to understand the behavior of the system, the characterization of the system. Am I tuning a Ferrari or a Model T? How does it respond? And so to do this, you have to do some dynamic testing, some bump testing. You got to move the output and see how the process variable responds. If I open the valve, what happens to the temperature? Does it go up? Does it go down? How fast does it move? All of these characteristics are generated from understanding the behavior of the system, from making dynamic changes. And a good test is very simple. The output moves in a clear and sharp fashion, and the process variable does something in that response, right? And so whether you do open loop testing or closed loop testing, they all kind of have that same kind of character, which is you make a change to either the set point or the output that ensures at least a 3% move of the valve. Why 3%? Odds are if you move a valve 3%, it's going to do something. If you tell the valve to move a 0.5%, probably not going to do anything. So 3% is a good kind of minimum, again, rule of thumb, right? You want it to move, you want to see a clear response to the process. Bad tests are things that the output ramps very, very slowly, or that it's tuned so conservatively such that when you make a set point change, the output appears to kind of ramp in one direction. That is not good data for analysis. We need a sharp change and a clear response, right? That's what we're after. And how you move the process really kind of depends. And Damien, what are some of your thoughts on the types of dynamics in the tests that we would run?
Yeah, again, it's this is fundamental to understanding your process. It's looking at this relationship. If you can understand how your process is reacting, the size of change, the speed of change, the delay of change, it gives you that understanding to be able to go, okay, we can do something with this. It's if again back to if it takes 15 minutes to change the temperature in this process, you won't do it in 5. You do have to be respectful of those numbers. You have to be respectful of the if it can respond in 30 seconds, well then it will certainly respond in 1.5 minutes. You don't have to go to the fast ones to do it. So getting this step test data, you're all used to looking at this because you look at process trends all the time. We're adding on this step test function to make sure that we can clearly see the relationship between that first the output change and the PV response. There's a number of ways of doing this, and if we just go to the next slide there, it's this step test. These are all step tests. They've all got a value to them. I always say I have to negotiate with myself and with operations as to what kind of step test I want to do, what size of step test. Bob said 3%. You need to clearly see the change. Now, if we look at those 3 step tests, one is in one direction, one is in 2 directions, the other one is in 3 directions. So we're getting more color to that information, and that color is going to be fundamental to how we benefit from that understanding of it, I suppose. The DLO there is the design level of operation. Where does this process operate? Where is it going to spend its life? If this is a fixed temperature, perfect. You just step around that process. The doublet test gives us the best color, because although the first and last steps were small, that step in the middle is large, and it also means that we can trust that the process will stabilize somewhere. If we make a small change initially, we can see it move. It may not be good enough to get clean, clear data, but it'll give us that confidence that when I start to step in the other direction, again, it's a negotiation with with the operations. Oh, you can't touch that. That's that's what they all say first. No, you can't touch that. I says, well, where are the alarms? Well, it's +5 and -7. So can I go +3 and -7 from there? You know, so I'm not touching the alarms, but I'm living in that range to find your perfect position. You know, that doublet test, I actually like a double doublet because it gives you that repeatable information. Bobby, again, the doublet is
Yeah,
that where you are?
that the doublet is where I live, and you know, it really gives you the most amount of dynamic information, and it allows you to do that negotiation with the operators, because nobody wants to allow you to do big tests. They want to give you the smallest test possible, and so you can kind of play the game to say, okay, well, I'll go 2% up but 4% down, and you get that 4% in the middle, and as Damien said, you double up on it, right? And what I like to do is I like to propose this doublet test as kind of the methodology to get the actual data that we're after. And so, Vera, if you can go to the next slide, this is the style of bump test that I tend to recommend, and it kind of leverages that doublet idea. And I start with set point changes, right? And I start with set point changes for a couple of reasons. One, gives me a baseline, right? Where is the current controller performance at, right? And then we can start with, okay, here's the current behavior, here's the control objective that we defined. What's the difference between those, right? Because every now and then you're going to be asked to tune a loop, and you look at the control objective and you look at the current performance, and you're like, it's perfect. It's doing exactly what it's supposed to. There's no work to be done. And so if you just immediately start jumping into tweaking numbers, you've just wasted an entire afternoon. So start with that set point change, establish the current performance. Where are we at? What are the changes that need to be made to align closer to the control objective? But the second part of that is it allows you to understand what the manual output changes are, right? If you need to do manual output tests, sometimes it's hard to understand what is a safe amount of controller output movement that I can apply and still maintain within the tolerances that the operator has set. So if you start with that kind of manual, that set point change, you can see those kind of colored arrows, the red, green, and orange arrows at the bottom, right? It'll tell you, okay, if you hold the output at the red and then go to the green and go to the orange, you're going to stay safe, relatively safe within the bounds. And so you repeat those, and then you do what Damien said, which is a double doublet, which is you do the same thing but in opposite directions. And so at the end of the day, you end up with at least 6 bump tests, right? 6 individual steps in different directions, some big, some small. It gives you information heating and cooling, opening and closing, different directions, both sides of the operational level. Gives you a ton of information. In fact, you could take a step back, and even this is a flow loop, you could use some of this to evaluate the quality of the valve. If you start and stop at the same valve position, in theory, you should be at the same flow. If your flow starts and stops at 2 different values, even though your valve's at the same value, you may need to go and investigate some of your equipment a little bit. So it gives you a whole bunch of information. Again, bump tests are designed to help you understand the characteristics of the system, right? And it's very important. Good data, good results.
That repeatable is so important. The PID is a linear device. It's just getting the information in. It doesn't always know where the valve is. So to make that lower trend there of that double doublet gives you that confidence that the valve is doing what it's been asked to do, and it's returning, even after all of those strokes, it's returning back to the same position and leaving the process variable at those same numbers. That is key to it. The negotiation, one thing I would say to the set point is really good at the start of a process if you don't know the process. But I say look back on the trend a week, a month, a year to see where does this process live. It lives between this range of operation. So you'll get a high degree of confidence as to where this process operates, and then you can design your step test to go through it. Next slide there, please. So once we've figured out how we want to get the data, we do need to confirm this data collection. Is the information that we're getting on our trend, correct? And the repeatability is going to show that correctness, I suppose. But is it representing all of those system dynamics? Is it giving us exactly what's happening to it? I like to look over a week or a month of data to see what went on you know, you can ask the question, why is the PV now running much higher or much lower, or the output is changed? Is there a load disturbance that's coming into that system? You know, because that's going to give you confidence to move into the tuning to work to it. You know, sample resolution is fundamental to it. Good data, good quality data is going to be key to that, because if you don't have good sample rates, you're not going to see all of the movement or motion that's in a process. You know, sufficient duration. Regularly, we get step test data that's incomplete. It's only showing a section of the information. It's not allowing it to settle out. So allowing the system to move to the new load position is very important. So you're seeing that overall time of the process. Noise, you cannot tune noise out of a process. Noise is something that just lives in a process. If you have noise, you need to go after the noise. If your noise is 1 degree of temperature oscillation, you cannot control that system at 0.5 or 0.1. It just won't control in there. So, you know, certainly instrument noise. Process noise has the same problem again, and it can be a flaw of tuning. Can we just tune that a bit more aggressive to stop those spikes there? But if those spikes are noise, process noise or instrument noise generated, it's going to be very hard to get them tuned out, and can cause you to push the aggressiveness up that curve to a point where you're tipping on the edge of trying to be responsive when you're not actually doing it. You know, disturbances and confounding variables. Bob, do you want to jump in on those confounding variables?
Yeah, and so the whole point of data collection is to understand the dynamics of the system, and you kind of take a very controller-centric point of view, which is how does the controller output impact the process variable? So that relationship needs to be relatively pure. It has to say the primary thing impacting that process variable has to be the controller output. And so if you have other variables that are driving that process variable up and down that are not the controller output, it's going to generate inaccurate models, inaccurate representations, right? Let's think about if you're trying to understand how fast a car accelerates and you're doing all of your testing down a 45% grade, that's not going to give you the true representation of how the car accelerates on a flat plane, right? And so you got to understand the dynamics and the disturbance of the system. The thing that's impacting the process variable needs to be the controller output, free of all the disturbances. Now, clearly it can't be free of all of them. The way I like to look at it is the primary thing moving the process variable is the controller output. So if you have disturbances that are, you know, bouncing the process around a little bit, make a big test to make sure you dominate over that. And then think about repeatability. Do multiple tests and make sure the same thing happens. One test isn't enough to confirm without a doubt that the dynamics are what they are. I did work back years ago on this level controller, and they're like, we can't get this thing to tune. So I said, let's do a bump test. And so we made a bump test. We increased the inflow into the tank. The level went down. I'm like, well, that's not right. We increased it again, then the level went up. We decreased it, the level went up, and it was just like almost completely random on what the controller output's influence was of the process variable. That would be very confusing for a PID controller. Think about trying to hit the gas and the brake and have it randomly change which one goes, right? Repeatability. Now, the issue with that had nothing to do with tuning. It was an anti-foaming agent system that wasn't working, so foam was getting created. But again, not a tuning problem. You got to understand that repeatability. And you got to think about that, you know, that adequate sample resolution. And so just a quick note on that on the next slide. So we always get this question is, how fast should you sample data? As fast as possible, right? I'd love to see 1 second data for everything. It's not a reality. Older DCSs don't necessarily have the throughput on their networks, but you know, flows and pressures, you're going to be wanting to look at 1 to 2 second data. Levels, depending on the size of the tank, 1 to 5 seconds. Like temperature loops, I like to say maybe closer to 5 seconds unless it's really, really, really slow. And so you want to think about the speed of the system, right? Data should be sampled 10 times faster than the process time constant, right? It's basically how fast it need to go. Think about driving in a car in a parking lot at 1 mile an hour that has no cars around you. If you opened your eyes for 1 out of every 5 seconds, you'd be okay, right? You probably wouldn't hit anything. Try to do that same thing on on the interstate, you're going to crash into something. So make sure you're sampling data at an appropriate rate, right? And that appropriate rate will help you understand the dynamics of the process. You want to understand the behavior, and Damien, any other thoughts on that?
Yeah. So sampling on from a practicality point of view, it doesn't mean you have to have a different sampling rate for every type of system, because in process manufacturing, we don't travel at light speed. The processes are multiples of seconds or minutes most likely in their time constants. So to sample at a consistent, it's very easy to say all our historians is sampled at 1 to 2 seconds, or some slow number, which is more than adequate for the majority of systems. Actually, I find the biggest one between the greenfield and the brownfield sites. Modern systems that have had an upgrade are now all on, yeah, we have 1 second data. That's our standard now, which has been really good for us and for tuning, because it means that consistency. Sometimes you have to negotiate and look for a slow rate and a fast rate, but from that information we can go and generate this model. The fundamental to this model is there's two kinds of models. There's a self-regulating model and a non-self-regulating model. Now, relatively new terms perhaps to some of the audience, but think about your processes. Which ones self-regulate? When you open the valve, energy comes into the system, but it doesn't go to 1,000,000 degrees. It ramps it up by a number of degrees or temperature and settles out at the new point. You can see, you've all seen curves of PVs responding to change, and they curve up. You're used to seeing this information. Just know that there's a self-regulating process, which is flow, pressure, temperature, pH, concentration, etc. And there's non-self-regulating systems, which is level. Think about the level system. If you have a tank of liquid and you increase the flow rate into it, what's going to happen? It's just going to start to ramp up, and it's a lovely linear straight line, but it will go forever, not to 1,000,000% in the tank. It will go to heartache or problems and all kinds of documents been written when you flood the bund on the process. But I said it just will continue to fill unless we sit at this balance point. The volume in equals the volume out, and tuning level control loops has to have that consideration. What is this tank used for? Why is this tank been put here? Most times they're buffers. We actually don't really care whether it's 50% or 55%, but there has been a habit to tune level controllers the same way we tune temperature controllers. But level control should have a nice float in it, respond and react, and don't flood the bund, but just to maintain the buffer. Some designer put the tank there as a buffer system, So we go to next slide.
Yeah, and so kind of build on that, right? The idea between these two dynamics is to try to understand the characterization, right? And you think about all the steps that we've done up till now, right? Define the objective, the purpose, the goal of that controller. Is it a surge tank? Is it not a surge tank, right? Then we understand the data collection. We want to try to make a change to the process. We want to make sure that the change in the data that we're collecting is good, right? And all of this leads us up to generating a model of the system, which gives us, hard characterization. It gives us model parameters. And those two types of systems, self-regulating, non-self-regulating, cover the breadth of pretty much all the types of processes that you're going to experience out in industry, right? And these two models, we can model these dynamics with first order models. They're very simple. Are they perfect? Of course not. They're not supposed to be perfect. All models are wrong, some are useful. The idea is that these give us enough information about the basics of the behavior of the system to be able to characterize it. And we need to make sure we characterize, flow loops differently than level loops. We need to match the models to the dynamics, right? It's all about understanding the behavior of a system. And so we can use the first order self-regulating model on things like flows and most pressure loops and continuous temperature controllers, stuff like that. And it gives us enough of the basic information: the process gain, time constant, dead time, how far, how fast, with how much delay. Now, how to calculate those, a little outside the scope of this webinar. Tons of materials on different webinars we've done and different websites out there. But it's getting those models is key, right? And with non-self-regulating systems, with level controllers, we're looking at an integrator gain and dead time, which is kind of the integrator gains a combination of the how far and how fast and delay. But these are all about characterizing the system. It's understanding the behavior of a system. We're applying some rigor to how we calculate the dynamics of the system. We're not trial and erroring it. We're trying to understand the behavior so we can get to the right answer. All right, generating these models is key. These models are what allow us to generate tuning parameters, understand the behavior of the system. If we're doing MPC or APC, we can use these. If we're doing things like dead time compensators, we can start to use these models in those equations. And so they become very, very important for us to understand those dynamics. And just as a side, you know, these different types of dynamics, they kind of cover a breadth of different stuff. And that non-self-regulating one, level is by far the most common, but there are other loops that can experience that. Anything you see that just kind of ramps in general in one direction is going to be integrating. So if you're doing, you know, a blanket pressure on top of a tank, right? That's actually an integrating process, and it's even more complicated because you got things like split range control that you have to deal with on the blanket. But you're increase the pressure into the tank, the pressure is going to increase until the pressure equals the pressure of the line. You bleed it, and the pressure is going to drop until the pressure equals the outside temperature or outside pressure. And so that's an integrating process. Some density controls and batch systems are going to be integrating. So think about the dynamics. And again, all that's going to come out of that bump testing that you do. You make the changes. You should be able to see kind of the response of the system to be able to understand what it's doing so you understand how to handle the dynamics of it, right? Again, we want to understand the behavior of the system, right? That's what it's about. Understand the objective, understand the data, understand the process, right?
It's back to that why am I here question. If you've answered all those questions at the start or filled in that information, when you get to this point, you're going, okay, I get this now. I have information now. I know how I wanted to use it. You know, the gain, time constant, dead time, that ratio, you've been looking at first order model generation all of your professional career. If you've ever looked at a trend, the information is in there. You just need to watch for those sharp output changes and see what the PV does with that, to see to look for those relationships. You know, that delta, the PV over output, it's that relationship, the time constant. You know, if this process takes 3 minutes or 3 hours to change, that's going to feed into how you're going to control it. So those, and the dead time is dead time. It's a very tough one to change if it's bad. You know, it's going to be a value that you're going to have to work with, or you're going to have to do a major design change, which is, you know, it doesn't happen. You know, it can, but you know, it's that delay from when we make a change till when we see the change. If that instrument is poorly located 10 meters or 50 meters down the pipe, that's dead time, and you're never going to be able to control or to accurately control. This is the killer of good control, perhaps, is a good definition on it. With all of that information, when we've pulled into it, we can then start to do tunings, you know, and from the tunings, we're back to this document, you know, the who, what, when, why, the why am I here question. How is it performing? Who, you know, what is it doing? What do we need it to change? Again, I always go to that why am I here? You've been pulled in front of this PID for some reason. Can you tune that loop, either for commissioning or through operations, and that it's not doing what we wanted to do? Analyzing that from trends, from operations discussions, pulling all that information and recording it to get that information. You know, then you can decide as to, you know, how is it running? You know, what do we want to do with it? And we need to record that. We need to record where is it currently. I, again, hands up many times in that manual tuning, the 50% that we had in the early days, you've gone, what tuning parameters did I use the last time on this one? Or, you know, I've moved the tuning parameters and I go, damn it, I can't remember which number did I change the last time. Recording that information is going to be so key to allow you to progress through a tuning efforts, you know, with all your with all of your steps and your answers, you know, so that you can then come to it. That when condition, when was the loop last adjusted? You know, in your documentation, in your processes, have you got a record of when these loops were changed last? You know, was it commissioning? 10 years ago? Was it last week? Was it post shutdown when a valve was changed or something? Understanding that is going to give you that information, and then why? Like, why am I here? And why was it changed? Is going to be the keys to it. Bob, have you a feed on that?
Yeah, I mean, it's all about saving your future self heartache, right? Having this documentation helps you understand what was done last time, and so you can start to see the process kind of unfold. Again, control narratives, man. I'm going to stand on that soapbox all day long. A documentation for the control loop, include history of tuning changes, right? When was this change? Was there a control objective change? Ultimately, you got to figure out why the behavior changed and document it. Hey, we had to tune this loop because they swapped a valve. Well, maybe that can start to trigger workflows that, hey, when they swap a valve, don't wait for the behavior to go poor because they swapped a valve. When you swap a valve, automatically fire an event to go and go do the tuning as part of it, right? You build the documentation to start build your workflows, build your process. I'm also a huge fan of historizing tuning parameters, right? No, I don't work for historian companies. I don't get a commission on the tags that you add to your system, but a history of all of those values is very, very critical, because there's nothing worse than coming in at 10 a.m. and like, oh, this loop just went crazy last night, right? And to have a history and go, well, yeah, because they changed the tunings at 2 in the morning. It was working fine before that. But if you don't have that history, you don't know, and you're left trying to diagnose a problem from the ground up, and it's wasting time, right? Save yourself future heartache. Document everything you do. Share that. Collaborate, and allow that information to make your job more efficient, right? It's really, really important. Documentation, and I know we're all terrible at it. I'm as terrible at it as everybody else is. I'm getting better, because if I don't write it down, I don't document it, I'm not going to remember it tomorrow. And so, a lot of the tools that are out there now are really designed for collaborative documentation, right? And that's really, really important, right? Which kind of takes us into our next survey question here, right? Which is really kind of focused on the challenges that you're going to experience, right? When you're tuning loops, what are the issues that you have, right? Is it, as Damien said, they don't want you to touch it, right? These loops are off limits. It ain't broken, don't fix it, right? Are there just loops that you've never been able to really muck with because they're too noisy? You can't really generate models. Even trial and error tuning doesn't work. The loops take too long, right? And those are the types of things. And Damien, you want to assess the bottom two there?
That loops taking too long is something that, well, it takes, for every step test, for every change, it takes 4 hours to do it, and they build, for every manual change in tuning parameters, you have to wait those times to see what it's doing. That's going to be a tough ask. It can change a tuning from minutes into weeks, I suppose. Too many controller types and different equations. The day is gone where there's just one vendor on site. They still exist, and there's still a good portion of them, but the likelihood is there's a number of different flavors, even within a vendor, I suppose. The testing and assessing the pros and cons, it's all about that, step test, understanding what we're trying to achieve is what's key to it. So taking those questions, let's see what the group have put their percentages on. Have we enough time, Vera? Is it
just 1 minute more.
Okay, yeah. So get your answers in there. Go ahead, Bob. Sorry.
Yeah, I was just going to say on that, can't assess pros and cons. It's always, you've gone and tuned the loop, and you have to document what improvement did you make. And if you don't have a good process to define the objective, it's hard to prove that you've made the process better or worse, right?
Yeah.
And I've definitely tuned loops before for customers, and we've gone to the controller objective, and we've tuned it towards it, and everybody's like, now we don't like it. Well, it's actually doing what it's supposed to do now, right? And here's the results. And I 50% they're difficult loops. Loops are noisy, long dead times, right? Which to me, those are loops that are difficult to tune. And those are loops where trial and error and making up tuning values can get you into trouble really, really quick, right? Simple loops are easy. unfortunately, there's a lot more to plants than just simple loops, right? There's a lot of complicated temperature and interacting concentration and levels and flows, and you've got processes are more complicated, and the loops again are more complicated.
Yeah. That's first one. Some loops are off limit to sensitivity. That's that negotiation to wit. There's a problem with this loop. We know there's a problem. We need to resolve it. We need to play with it, to understand how it's interacting, or understand how the speed of it to do work. But if you have that process, if you have that consistent, repeatable process that's recording, and you've built up a knowledge and an experience, and also, let's be honest, a trust with operations that you're going to follow this procedure. It's the final one that can't assess the pros and cons. An automation engineer once said to me, there's two kinds of famous in the world. There's good famous and bad famous. And nobody likes to be the bad famous. So, getting the information and making good decisions so that you can be that good famous is what it's all about, I suppose. So there's some nice, interesting numbers there. But they would also feed back into that original statistic about 20% of loops in manual. It's better, we can't control it, so we just leave it in manual, and that's where that 18% of sensitivity comes from. We know if we run it at 42% output, it just sits there, but it's not ideal, I suppose. So interesting values coming back from that. Thanks, Vera. So just to kind of recap on this, to go through the process, we've talked about lots of things through that, and then we're kind of machine gunning you with information, but just to kind of come back in and go, so developing your skills is fundamental. Developing a routine to it that you're going to use the standard method each time. You become consistent with your process. That follow a process, find, define, understand, tune, test, and document. That's going to be key to that. My recipe for tuning is going to give you that. Consistency in results is going to be because your consistency with that process. You're going to follow that procedure. Why am I here? Look at the trend, talk to ops, understand where the problem is, then do some testing to find out where my limits are, and use that then to start making decisions on it. You may come up with a decision. There's a problem in this loop. It's a valve. There's a mechanical issue here. There's an instrument problem. That takes that into the, so that you find these poor performance. Say that loop can't be tuned until we do this. We need to address the sticky valve, the sloppy valve, the non-linear valve, perhaps. Bob, you want to take it up from there?
Yeah, I mean, it's really, again, I'm going to reiterate the first one, which is skills and knowledge, right? Make sure you're trained, that you have the necessary information to be able to tune loops and do your tuning process effectively and repeatably, right? Pursue that consistency. As I mentioned earlier, you give 15 people with not a lot of training tuning loops, you're going to get 15 different answers. You give people a process to follow, you give them training, they're all going to generate the same results, right? You use software, you can leverage tools to make that process easier. Tools are not a replacement for knowledge. Tools are force multipliers, right? You got to have the skills and the knowledge. The tools then allow that skills and knowledge to be a much stronger multiplier. Then make sure that you're monitoring, make sure you keep track of the information, right? Document your wins and successes, right? You want to be the good type of famous. You want to be the person that fixed a bunch of loops, that improved performance, that identified issues, corrected them, and shared that, right? And you will be the good type of famous, right? No good deed goes unrewarded, because if you start tuning a bunch of loops well, you know what you're going to end up having to do? Tune a bunch of loops, right? But it's fun, right? You get to go out, you get to improve it, but make sure you document everything, right? And keep your improvements, make sure you monitor your performance, identify the opportunities, be proactive with the loops. These things are the heartbeat of your plant. Make sure that the control loops are working correctly. And we'll just kind of round it up with the last survey before we hop over to the questions. What can we do to help, right? What are the things that we can do to help you. We've got tuning guides that we can send out. We teach loop tuning training sessions, both on-site and virtually. Me and Damien teach a ton of these each year. And they do a good job of explaining the information, walking through the by hand approach for tuning using tools, by hand, models, step tests, all of that stuff. We can
It
get
will give you that recipe. You know, our training class is fundamentally based around good tuning process. You know, having a process that works every time, all the time. You follow it, you get good tuning results out of it. Vera, have we got many questions coming in? I'm just seeing the time there. We can probably slip a little over if we're good, but
yeah, we have 3 questions actually.
Okay.
So I'm gonna do the first one here.
Okay, just close out. Do you want to close out the poll, or I'll let the poll run, I suppose. Yes.
Yeah, I will let the poll run, and I will do just the first question, and then I close the poll. So, how can bump test be done if the input of raw material change, like solid percent, water percent, raw material temperature? Should bump be done on worst case raw material or more normal raw material?
So that's a good one, and it really, I have my my recommendation is to try to do bump tests in a couple of different scenarios, right? Clearly the worst case, clearly the normal, to determine what the difference in dynamics are. Because if the behavior is significantly different, you may have to employ something like adaptive control that would change the tunings based off of that material that you're feeding into the system, right? You could do kind of a recipe-based tuning approach, and we've done that a lot for like consumer products and so forth. Because if the dynamics change dramatically, no one set of tunings are going to work, right? It really just kind of depends on the difference. But set the objective, do your bump tests, do a couple of different ones to try to understand how the dynamics change. My rule of thumb, if the tunings change or the model, the dynamics change by about 2 to 3 times from the different ranges, 2 to 3x, you can generally just average the tunings and be okay. If it's more than 3 times, like the process gain is more than 3 times, you may want to start investigating things like adaptive control to change the tunings. But you're spot on to kind of recognize it's the feed. So can you analyze different feed settings to see if there's different tunings that may be optimal for those? And it just depends on how different the dynamics are.
Gain scheduling, Bob, is one of the most underused tuning optimization opportunities, I suppose. You know, adapting your tunings as to where you operate, or with the varying different materials coming in. If you know you have a consistency, you need to go after and understand the inconsistency. You know, if you can define and measure that coming towards your process, knowing, is it time of year perhaps? Is it outside air temperature? You know, it's depending on where your materials are coming from. If you can define it, then you can say, in this mode, we're going to operate this set of tuning parameters. In the next mode, it's really understanding each one of those modes of operation, as Bob said.
Yeah, absolutely. Good question.
Yeah. The next one is, how does the modeling differ for chemical injection control?
So for chemical injection, if you're talking about the individual flows into the system, right? So sometimes with chemical injection, it's all about like ratio and blending application. So you may have a bunch of these feeds that have to come in at a very specific flow rate to match whatever your recipe is. One of the things that's really important with blending and ratio control when you're doing those types of injection is that the ratio, how each of those controllers respond, needs to be exactly the same. You can't have one of your chemicals come in and go from target A to target B faster than the other ones, because during that kind of change, you're going to have an imbalance in ratio. And so again, understand dynamics, understand the objective, but when you're doing that kind of that ratio, that blending, that when you go from set point A to set point B, the response times of each of those controllers need to be exactly the same. So you go from set point A to set point B, all 5 or 6 of your injections all move at the same speed. You don't have an imbalance at that. Generally, injection is going to be flow, maybe pressure, And so you should be able to follow kind of the basic process of those, but you need to understand kind of what the overall goal of those types of systems are.
I'm not going to get in on that one, Vera. I think Bob covered it well. It's a tough one. It is a tough one, but sorry, next question.
Yeah. Okay, so what is the recommendation for tuning processes that have a regenerator? When do you do a pump up? It takes a long time to get stable and does not really follow the CV of the valve. Heating temperatures goes up, which will result on inlet temperature rising because of the regenerator.
The regulatory, yeah. So this is probably, I'm guessing based off the question, kind of like slow temperature loops. So things where you've got, you're trying to heat up, large vessels, right? And whether you're doing heating elements, you're doing heating flows like hot liquids, hot material through a jacket. You're making changes. The temperature doesn't necessarily move very, very quickly, and it tends to kind of ramp in one direction. There are approaches. They're not truly regulating processes, self-regulating processes. They're kind of a hybrid. There are some shortcuts, and feel free to kind of reach out afterwards. We can send some information on the shortcut, but you can look at the changes and that kind of initial dynamic response. You can treat it as integrating, and you can kind of do some shortcuts. We use this a lot in like batch temperature control and furnace control, where you've got very, very slow systems. Outputs move, but they may not be precisely the response. It's not just a simple flow of some simple temperature. It could be driving, SSRs and heating elements and things that may not move very quickly like you would expect them to. And so there are some shortcuts, there are some processes, and we'd be happy to hear a little bit more about your application in specific to get you some better information.
You have to remember that the load change from ramping up to get up, the delta T on that system is huge, and you're throwing energy at it initially. So if you're using a pure PID for that, once you get up there, it's going to overshoot. It's going to start oscillating on a very long cycle. So the rate of heat addition and the rate of heat maintenance are going to have two different values on it. So you have to almost schedule that so that you're going to start aggressively, but as you close that delta T, you kind of dampen off that process and finding an aggressive start to get it moving, and then a more conservative when you get into a closer range on it. But yes, we can certainly send some information. Yeah. One more question maybe, Vera?
Yeah, we have one more question. We are already late, so I think that's the last one. So are you against tuning using past process data? Are steps tests a must for tuning?
So go ahead, Bob.
I was just going to say for historical data, right? Is that what I heard?
No.
Yeah, it was against tuning using past process data. Are step tests a must for tuning? Is the question.
Okay, I'll let you do this one, Damien.
Yeah, so okay, two scenarios. You've changed a process, and you've put in a new process, and you're robbing the tuning parameters from the equipment next door in and put them in here. It's a quick practice, and you see it a lot with equipment that is iterated. You've multiple air handlers, multiple production lines, multiple vessels. You do need to confirm operation, I suppose, because no equipment is identical. It's certainly a good place to start, perhaps is where, but you would need to do an exercise of that process to confirm that it's acceptable, that it's responding. And putting the tuning parameters in is going, oh yeah, it's controlling at our 72 degrees. You need to exercise that process. You need to change the set point. You need to change the load to see, is it appropriate? So the short answer is yes, you can, but the long answer is you do need to think about, does it do what you want it to do? I suppose the iteration of it is a good quick way to get going, but is it a long-term solution? I would question. You'd have to get a model so that you know where it is. Bob, do you want to feed into that one?
Yeah, I mean, with historical data, you need to understand the context to which this historical data was captured, right? Is it normal? Is it how it operated 6 months ago, similar to today? Is there bump tests from 6 months ago? And if so, are those still relevant today? Or, 6 months ago was January and now it's July, so the dynamics aren't necessarily equal. So historical data is okay as long as you understand the context to which that data was collected, and that the behavior of the system is somewhat similar 6 months ago as it is today. Obviously, if it's from last week and it's normal, go for it, right? If it's good, it's sampled well, historical data is good. You do need set point changes. You do need bump tests in that data to reveal the dynamics. Constant set point data is not good for analyzing. You do need bumps, but historical data is great. I use it all the time as long as the context, the behavior of the system is the same. And I know we've gone way over at this point, so.
Thank you very much. So let's things here. We are heading to the end, guys. So for you that are going to the automation fair, we are going to be there too. So make sure to stop by our booth and talk with us. We are going to be there on Tuesday, Wednesday, and Thursday. Also, we will have lots of webinars on 2025. We are covering these topics like process control best practice, PID controller modeling tuning, plant-wide monitoring and analytics, performance benchmarking. So keep following us. We will always be promoting the webinars on our LinkedIn by email marketing as well. And if you have any questions, if you want to talk to us, please contact our specialists here. You can just read the QR code that goes directly to our contact page in our website. And thank you very much for participating. Have a great day.
Thank you. Bye-bye.
Thank you. Thanks, everyone.